Howdy. I wanted to present to you the concept of increasing through C. This concept elegantly describes what it means to have a positive derivative at a point. But really we're also talking about decreasing through C, because everything that we say here could have easily applied to a function with all of the signs reversed. So we're going to start with a definition. And we're going to say that f of x is increasing through C if f of x is greater than f of c, or x greater than c, but f of x is less than f of c, or x less than c, and all of this in a neighborhood, an open neighborhood around C. So this is our definition. Now let's get a clear graphical understanding of what we're talking about. If this is our point C and this is our value f of c right here, what we're saying is that my points that are to the left lie below, and the points that are to the right lie above. In other words, if I draw myself a nice straight line through C, then I can find a neighborhood around C so that all of my points to the right are going to be above f of c, and all of my points to the left are going to be below f of c. Please notice that there is no guarantee. F is not necessarily increasing on the entire interval c minus delta to c plus delta. You can see in the function that I've drawn here that my green part right here wiggles up and down. It's not increasing on the entire interval. It's just that all the points that are to the right lie above and all the points to the left lie below. So that's going to be our slogan for increasing through C. Points to the right lie above, and points to the left lie below. And it's entirely possible that this may be the best that we can say about f of x. It may not be possible to say that f is increasing on any particular interval. In fact, I will show you at the end an example of one such function. All right? And now I'm going to make a really simple claim. But first, I want to observe that everything that we've said about increasing through C could easily be rewritten in terms of decreasing through C. We would say that f is decreasing through C if points to the right lie below, that is, if f of x is less than f of c for x is greater than c. And points to the left lie above. That is, if f of x is greater than f of c when x is less than c. Okay, that's our definition. Now what I'd like to do with this definition is to make a simple claim, and that is that if f prime of c is a positive value, then f is increasing through c. Again, I want to be clear that if f prime of c is greater than 0, that does not guarantee me that f is going to be increasing on any interval containing c, just that f is increasing through c. Now, the proof is actually really simple. Let's suppose that f prime of c is equal to some value d which is positive. Well, applying our definition of derivative, that immediately means that the limit as x goes to c of f of x minus f of c all over x minus c is equal to d, which again is a positive number. And going back to what it means to be a limit, that means that there is a delta, that for any epsilon greater than 0, there is a delta greater than 0, so that when x is in the delta neighborhood of c, notice how I wrote that, then this quantity, f of x minus f of c over x minus c, is in the delta neighborhood, the epsilon neighborhood of d. And unfortunately, with my bad handwriting, the exists here looks kind of like the epsilon there, but they're not supposed to be the same. So let's actually rewrite this so it's a little clearer. What I'm really saying is that d minus epsilon is a lower bound for this quantity for the difference quotient, and d plus epsilon is an upper bound. So here's the deal. This is true for any epsilon, so we're going to choose an epsilon that is small enough so that d minus epsilon is still a positive number. And so what we have then is that the difference quotient itself is a positive number. And that can only happen in two ways. Let's take those two cases. One way is if the top is positive and the bottom is positive. But if the top is positive, then that immediately means that f of x is bigger than f of c. And if the bottom is positive, then that means that x is bigger than c. So that we see that if my derivative is positive and x is bigger than c, that forces f of x to be bigger than f of c, which means that f is increasing through c on the right-hand side. And in my second case, I can have a positive quotient if f of x minus f of c is negative, and if x minus c is negative also. But that would imply that f of x is less than f of c, and x is less than c as well. So that we see that whenever x is less than c, then f of x has to be less than f of c. In other words, for every single c value in the neighborhood c minus delta to c plus delta, except for x equals c itself, then we have f of x is increasing through c. Well, in some sense, that's kind of it. But I would like to show you a really intriguing function that illustrates what I'm talking about here. I should mention that the terminology increasing through c and this particular function that I'm about to use are both due to an acquaintance of mine, Lou Talman, who teaches math and is also part of the AP community. And he suggested this notation, and so I picked it up and I followed it. And the function, the example that he gives is the function f of x equals x plus x squared times sine of 1 over x. Ah, here comes trouble. Now this definition is obviously only valid for x is not equal to 0, and then we're going to let f of x, f of 0, be 0 itself. So here's our function. And now we're interested in its derivative. And when we compute the derivative, we have to compute the derivative of the top piece, and that's going to be 1 plus, now we need product rule, so first times the derivative of the second, and don't forget that derivative of the inside, plus the second times the derivative of the first. Let's clean that up a little bit, and what we get is 1 minus cosine of 1 over x plus 2x sine 1 over x. Well, that's fine for x not equal to 0, but what about at x equals 0? At x equals 0, I have to compute the derivative using the definition of the derivative, because my function is not equal, but my function is a piecewise function in any neighborhood containing 0. And so I'm going to do that as the limit as x goes to 0 of f minus f of 0 all over x minus 0. But then that turns out to be an easy computation, because I get the limit as x goes to 0 of x plus x squared sine 1 over x minus 0 all over x. And we have a delightful common factor that cancels, so that I get the limit as x goes to 0 of 1 plus x sine 1 over x. You may remember doing the second limit before, but in case you don't, we're going to pull off a substitution of w equals 1 over x. And so that's the limit as w goes to positive, as w goes to infinity, of sine w over w. And using the squeeze theorem, we get 0. So what is the outcome? The outcome is that my derivative is equal to, let's put it all together, is equal to 1 minus cosine of 1 over x plus x, 2x sine of 1 over x, when x is not 0, and my derivative is equal to 1 when x is equal to 0. What's fascinating about this particular derivative is that it is not continuous at x equals 0. It exists at x equals 0, but it is not continuous at x equals 0. We have to actually work hard to find derivatives that are not continuous. Now, what does that mean for us? In fact, this term in the derivative right here is the problem, because this term right here becomes infinitely wiggly in any neighborhood of 0. And that means that my derivative is going to change signs an infinite number of times in any neighborhood containing 0. But, despite that awful behavior, it still has the nice property that right at x equals 0, all of my points, here comes my curve that's infinitely wiggly here, and then it's infinitely wiggly here, it still has the nice property that if I draw the horizontal line through f of 0, all the points to the right of 0 lie above, and all the points to the left of 0 lie below. And I know this because f prime of 0 is a positive number. Since f prime of 0 is positive, therefore f of x is greater than f of 0 for x greater than 0. And f of x is less than f of 0 for x less than 0. Even though there is no neighborhood containing 0 for which f is an increasing function. Well, I hope you enjoyed this exotic example, and I want to reiterate our basic theorem here, and that is that if f prime is a positive number, f is increasing through c. And I don't think it takes too much imagination to see that the converse is also true. If f prime is less than 0, then f is decreasing.